Hello everybody. Today we are going to be talking about zeros and multiplicity. So our objectives for today are that students will be able to identify the zeros of polynomial functions by graphing, write polynomials in factored form, describe the effect of multiplicity on the graph of a polynomial function. Let's get started. When we're talking about the zeros of a polynomial function, we're talking about the points at which the function intersects the x-axis. A polynomial function of degree n can have at most n real zeros. So if a polynomial has a degree of 3, it can have at most 3 real zeros. An even polynomial has an even number of zeros, or it has no zeros at all. And an odd degree polynomial has an odd number of zeros. Let's continue. So what does that mean when we're graphing a function? How do we identify the zeros by graphing? What I want you guys to do is to definitely use Desmos to graph these polynomial functions, and then you would get a graph that looks like this. We see that it's a third degree polynomial. Therefore, we know it could have at most 3 real zeros. When we're looking at this graph here, our zeros are wherever it crosses our x-axis. So the points at which it crosses the x-axis would be -2, 0, 0, 0, and 1, 0. So these are going to be our zeros of the polynomial function, and that's how we can quickly identify them by graphing. So we would say that x equals, and we're going to use the x values, -2, 0, and 1, because those are the x coordinates of each of our zeros. Therefore, all of our solutions are -2, 0, and 1. The linear factors of a polynomial also reveal its zeros. So the linear factors can be found by writing the polynomial in factored form. So for number 3, if we want to write f of x equals x to the third minus 2x squared minus 15x in factored form, so we want to factor this polynomial, the first thing we want to do is ask ourselves, is there a GCF? The answer is yes. So we can take out an x. So f of x equals, take out an x from the polynomial. Then what we want to do is try to factor this quadratic that's left inside the parentheses. So start by doing our diamond, -15 on top, -2 on the bottom. Two numbers that multiply -15 add up to -2 would be -5, +3. So we're left with x minus 5, x plus 3, and don't forget to bring down this x. So if we were to write this in factored form, our function would be f of x equals x times x minus 5 times x plus 3. Now what we want to do is set each of these equal to 0. So we would say x equals 0, x minus 5 equals 0, x plus 3 equals 0. So we know x has to equal 0, add 5 to both sides, x equals 5, subtract 3 from both sides of this equation, x equals -3. So if we were to answer the question, what are the zeros here? All right, what are the zeros? We would want to write our final answer. Oops, let me move this up a little bit. Our final answer, we would want to write it as x equals -3, 0, and 5. And we always write it from least to greatest. Those are the zeros of this polynomial function. And we can easily identify them by factoring out our polynomial or writing our polynomial in factored form. When we're talking about the multiplicity of a zero, the multiplicity is equal to the number of times its corresponding linear factors occur. So let's take number 4 as an example. First thing we want to do is write this function in factored form. So first things first, take out a GCF. All right, so, oops, let me get my pen. F of x, we can take out an x squared minus 6x plus 9. Then we want to factor what's inside the parentheses. We do our diamond, 9, negative 6. Two numbers that multiply to 9 add up to negative 6 would be negative 3 and negative 3. So we're left with x times x minus 3 times x minus 3. Another way we can write this is x times x minus 3 squared. Now this squared here tells us that x minus 3 occurs twice. So when we set x equal to 0 and we set x minus 3 equal to 0, whatever we get, our root of x minus 3, so if we set, let's see, I need more space here. I'm moving down, not enough space. So if we set x equal to 0, we set x minus 3 equal to 0, one of our zeros is 0. Add 3 to both sides. Our other 0 is positive 3. However, because x minus 3 occurred twice, we would say x equals 3 multiplicity 2 because it occurs twice. So this squared right here tells us that x minus 3 occurs twice, as we can see when we wrote it in factored form. Therefore, the 0 of 3 occurs twice as well. So if we were to fill in this blank right here, what are the zeros and their multiplicity? We would say that x equals 0, multiplicity 1, because it only occurs once, and we would say that x equals 3, multiplicity 2, because it occurs twice. And the multiplicity of a 0 will affect the graph, and we're going to learn about that next. All right, so how exactly does multiplicity affect the graph? So for question number 5, we have the same polynomial function that we did in question number 4, and we found out that the zeros are x equals 0 with multiplicity 1, x equals 3 with multiplicity 2. When we take our graph, when we plug it into Desmos and we get our graph, we see that in fact our graph crosses the x-axis at 0 and at 3. How does multiplicity affect the graph? So when we look at multiplicity when we have an odd multiplicity, so when multiplicity is 1, multiplicity is 3, 5, just like this one right here. When multiplicity is odd, then the graph intersects or crosses at that 0. Okay, you can say intersects, you can say crosses, same thing. We see that it goes through the 0. When the multiplicity is even, just like this one right here, when x equals 3, multiplicity 2, we see that the graph touches the 0 and then bounces back up. So we say when multiplicity is even, the graph bounces at that 0. Okay? So this is very important for us. This is how multiplicity affects a graph. That's why it's very important to identify the multiplicity of a 0. All right, here's an example problem where we're given this polynomial function. We want to identify the zeros and state their multiplicities and describe the effect it has on the graph. So start first by factoring. We want to take out a GCF, which would be x squared. So x squared, we're left with x squared minus 2x minus 8. We do our diamond, negative 8 on top, negative 2 on bottom. Two numbers that multiply to negative 8 add up to negative 2 would be negative 4 and positive 2. We're left with x squared times x minus 4 times x plus 2. Set each of these equal to 0. So x squared equals 0, x minus 4 equals 0, x plus 2 equals 0. So when we're talking about this one right here, we take the square root of both sides. We're left with x equals 0. However, our 0 is 0, but its multiplicity 2. because x was squared. Therefore, the effect on the graph is that it's going to bounce. All right, when we're talking about x minus 4 right here, so we add 4 to both sides, add 4 to both sides. Our 0 is 4. It only occurs once, so it's multiplicity of 1, and we know that it's going to cross or intersect. Last but not least, subtract 2 from both sides. Our 0 is negative 2. It only occurs once, and it's just going to cross through this 0. All right, you could also see a problem that looks like this, where you're given that a polynomial function has a 0 at negative 6 with multiplicity 2, and it has a 0 at 2, multiplicity 1. We want to write a polynomial function in standard form that could represent this function. So start by knowing that the 0 is at negative 6 with multiplicity 2. If the 0 is at negative 6, the factor is going to be x plus 6, because it's going to be the opposite. And we know it's multiplicity 2, so we have to square it. Then if we have a 0 at 2, the factor, if the 0 is at 2, would be x minus 2. It's always going to be the opposite. And it's multiplicity 1. All right, so you can either put a 1 there, or you don't even have to put it. Now we know this is a function. It's a polynomial function, so don't forget to write f of x equals in front. Now we want it in standard form, so we need to multiply this out. We can't leave it in factored form. So we would rewrite this as x plus 6 times x plus 6 times x minus 2. And then FOIL out these first two. So we get x squared plus 12x plus 36. Because if we were to FOIL the outside, inside, we would get 6x plus 6x, so we get 12x in the middle. Don't forget that x minus 2 over here. Don't forget to bring it down. All right, now let me scoot it up so we have some more room. Now we have to distribute this x minus 2 to every term in this parenthesis. So start with x times x squared gives us x to the third plus 12x squared plus 36x. Then multiply negative 2 by everything in the first parentheses. So we get negative 2x squared minus 24x minus 72. All right, and just like what we learned last chapter, I told you guys, write like terms in columns underneath each other, so then it's easy to combine like terms. So we're left with x to the third plus 10x squared plus 12x minus 72. And this would be our function in standard form that has a 0 at negative 6 with multiplicity 2 and a 0 at 2 with multiplicity 1. This would be your final answer. Now, the last thing I want you to be able to do, this is kind of pulling together everything we've learned so far about the graphs of polynomials, is if you're given a polynomial function and you're given the graph, I want you to be able to identify the turning points. So the turning points, if you recall, are your maximum and minimums, the increasing intervals, the decreasing intervals, domain, range, what are the zeros, so where does it cross the x-axis, which is what we learned today, what is the end behavior like, and what is the parent function of this polynomial. So here's an example. Let's start with the turning points. So if we're looking at the turning points, our maximum is the highest point of the hills, minimum is the lowest point of the valleys. So if we were to write our turning points, our turning point of this graph is going to be, first we have our maximum, which is negative 3.16, 3.08. That would be our first relative maximum. Then if we're looking at our relative minimum, it's going to be this point right here. So our relative minimum is going to be negative 0.85, negative 3.08. Now our increasing intervals. When is our skier going up the hill? So skier is going up the hill from negative infinity all the way up until 3.15. We use that x coordinate. So that is an increasing interval. Our skier is also going up the hill from this point right here to infinity. So we say from negative 0.85 to infinity. Now our decreasing intervals. The only time our skier is going down the hill is from this point to here. So our decreasing interval would be from negative 3.16 to negative 0.085, or negative 0.85. All right, so that would be our decreasing interval. So let's write that in. Oops, that would be 6. Got it round correctly. And we only have one decreasing interval for this graph. Now, the domain is going to be all real numbers because it goes from left to right at every point on the x-axis. So we say from negative infinity to positive infinity, or you could use the all real number symbol. And our range is going to be all real numbers as well because it goes up and down on the y-axis. Hits every point from negative infinity to positive infinity. So we say negative infinity to positive infinity, or you could use the all real number symbol. Now our zeros. Our zeros are going to be where it crosses our x-axis. So this polynomial function crosses the x-axis at this point, and this point. And when we're talking about the zeros, we want to use the x-coordinates. So we're saying it crosses, here's a 0, there's a 0, and there's a 0. So x equals negative 4, negative 2, and 0. Now our end behavior. So let me get my pen back. As x is approaching negative infinity, so as our graph is going to the left, f of x is going down. So our y-axis is going down, so it's approaching negative infinity. As x is approaching positive infinity, so as the graph is going to the right, f of x is approaching positive infinity because it's going up. So this is a good review of end behavior. And last but not least, the parent function of this graph is we always want to look at the highest degree, so we know it's a cubic function. So the parent function would be f of x equals x to the third. We know it's a John Travolta style graph. All right, so I hope you learned a little bit about zeros and multiplicities of graphs today, and it was a good review on identifying all the key components of the graph of a polynomial function. Look to your teacher or look to the board to see what to do next, and I hope you have a great day.